Hey, most excellent rock buds, Papa here. Hope you guys are doing fantastic. Today, we're going to look at the rocks that are generated by the different kinds of tectonic activities. First, we'll go over the about 4 major tectonic activities that I know of. We'll look at them and we'll see how they progress and what kind of rocks they produce, and we'll talk about why. Also, we'll have some examples of each kind, so stay tuned for that. If this video is helpful, please subscribe, and thanks a million to all you wonderful people who have subscribed. Okay, so here we go. The rocks of plate tectonics. We are talking about continental rifting, superplumes, subduction, and the ever-popular continental crashing. Let's take a look at continental rifting first. Here is supercontinent Rodinia about 1 billion years ago, and it is getting ready to rift apart. In this side view of Rodinia, you can see the reddish-orange mantle, which is made of mafic and ultramafic rocks. These rocks are dark, heavy, and full of iron, magnesium, and calcium. And above the mantle, you can see the tannish-colored land crust. It's made mostly of granite and granite gneiss, very felsic rocks that are lightweight and light in color. They're very quartz-rich and iron and magnesium poor. During the rifting process, this mafic magma begins to rise up, splitting the continent in two, and this magma is made of gabbro, a mafic rock, and as it gets closer to the surface, diabase, another mafic rock with the same mineral composition as gabbro. It just has smaller mineral crystals than gabbro. Hey, rock buds, as you may figure out, all that hot magma has got to rise up through a big, thick hunk of land crust that's very felsic. Let's see what happens. As the mafic magma rises up through the land crust, some of it mixes with the felsic land crust to form intermediate and felsic magmas and lavas. After all the land crust is eaten up and transformed, then you get massive eruptions of mafic basalt lava in far greater amounts than the felsic and intermediate lavas. In other words, with continental rifting, you get a little bit of felsic magma lava, a little bit of intermediate magma lava, and a huge amount of mafic magma lava. Doesn't always happen this way, but for the most part, mafic magma and lava dominate rifting events. So let's take a look at some of the rocks associated with continental rifting events. Here's some granite that represents cooled felsic magma, and some rhyolite lava that happens when the granite erupts onto the surface. Also, here's some dacite, a lava equivalent of granite, which just means when granite magma erupts on the surface, they now call it rhyolite and or dacite lava. Same mineral composition. And now we're looking at diorite, which represents intermediate magma, and its above ground equivalent andesite lava. But the real stars of the show when it comes to continental rifting are mafic rocks. We're talking about gabbro deep down, diabase close to the surface, and of course basalt lava erupting on the surface. When Pangaea supercontinent rifted apart about 250 million years ago, basalt lava flowed out in huge masses covering 800,000 square miles, and this eruption lasted for 1 to 2 million years, and it is now called the Siberian Traps, obviously located in Siberia. Hey guys, let's look at an example of continental rifting closer to home. This is Mount Rogers in Virginia. It is part of the National Forest. I believe it's the George Washington National Forest. When supercontinent Rodinia rifted apart between 750 and 550 million years ago, a lot of rhyolite was produced here. Mount Rogers is made mostly of this rhyolite. It is a felsic lava. And now we are in Shenandoah National Park in Virginia, and we're looking at the Catoctin greenstone. This is columnar basalt that was produced en masse as Rodinia rifted apart. And the crashing events that came after this metamorphosed this basalt into greenstone. The green minerals here are epidote and chlorite. Hey guys, so our takeaway here is that continental rifting produces mostly mafic rocks like gabbro, diabase, and basalt. Now let's take a look at subduction. Subduction happens when one piece of crust is shoved down beneath another piece of crust and dips down into the mantle. In this picture, we have the case where a piece of ocean crust has subducted beneath another piece of ocean crust. And as you know, ocean crust is made of mafic rocks. And by the way, as you know, this subduction happened because way across the ocean, a rifting event occurred which was creating new ocean crust and shoving the ocean crust against itself, and it broke and one piece subducted again, beneath the other. Billions of gallons of ocean water are being taken down into the mantle by the subducting ocean crust. All this ocean water greatly facilitates something called fractional melting. Let's have a look at that. A volcanic island chain is being created by this subduction event. Let's take a closer look of the volcanic island. In this side view of a volcanic island, we see the black piece of subducting ocean crust. On the left, it's diving down into the molten mantle and melting there. The dark blue color is the ocean and the light blue color is the sky. And even though the subducting ocean crust is made completely of mafic rock that's being melted into mafic magma, all the ocean water that goes down with it helps to separate out intermediate magma and felsic magma. The felsic magma, which is the lightest, rises up to the top of the volcano, and the intermediate magma, which is next lightest, rises up above the mafic magma. The felsic magma, which is granitic in nature, plugs the top of the volcano because it doesn't want to flow out. Eventually the volcano explodes and most of that felsic magma turns into felsic tuff and is spewed all over the countryside. So the generalization here is that when you have ocean crust subducted beneath ocean crust, you get a mixture of felsic, intermediate, and mafic rocks, very possibly with the intermediate rocks dominating as far as the volume goes. The Carolina superterrane that's located in North Carolina, South Carolina, and Georgia is a good example of ocean crust subducted beneath ocean crust. The Carolina superterrane is loaded with biotite gneiss and biotite hornblende gneiss. These are metamorphic rocks that began as diorite and andesite, both intermediate volcanic rocks. Another example of this kind of ocean crust subducted beneath ocean crust is Sierra Buttes in Northern California. The Sierra Buttes were formed when ocean crust subducted beneath ocean crust in the Proto-Pacific Ocean during Devonian times. The volcanic island chain was created and it crashed into Northern California during the Nevada orogeny. That was 150 million years ago. And Wikipedia says that andesitic breccia is the predominant rock there. This is an intermediate lava type. Now, rock buds, let's look at the case where ocean crust subducts beneath the edge of a continent instead of beneath another piece of ocean crust.
The mafic ocean crust subducts beneath the felsic land crust, and there's a pile of this felsic land crust. So once again, you get a mix of mafic, intermediate, and felsic magmas and lavas. And in this case, the probability is high that you're going to get a preponderance of intermediate to felsic magma lava.
So why in this case of subduction do you get a preponderance of felsic and intermediate magmas and lavas? Well, it's because once again there's a lot of water that goes down into the subduction trench with the mafic ocean crust, and that facilitates the fractioning of this mafic magma into intermediate and felsic magmas. And also in this case there's a huge piece of land crust just above all this boiling mafic magma, and so it contributes quite a bit of felsic and intermediate elements and minerals to the mix.
A super example of ocean crust subducted beneath land crust is the Sierra Nevada mountain range in California. These mountains were formed during the Nevadan orogeny about 170 million years ago, and then exposed by block faulting during the latter part of the Laramide orogeny between 70 and 40 million years ago. These gorgeous mountains are chock full of granodiorite, which is a rock that's kind of in between granite and diorite in its rock reaction. And monzonite, which is another felsic/intermediate hybrid kind of granite that is poor in quartz but very rich in potassium feldspar and sodium feldspar.
Hey rock buds, now let's take a look at the kind of magmas and lavas produced by mantle superplumes.
Hey guys, you likely remember from the video on Yellowstone that a superplume is a mantle plume that starts right about the core mantle boundary. The superplume is a scalding hot blob of ultramafic and mafic magma that works its way up to the crust where it erupts. If this superplume erupts into an ocean, you get islands that are made almost exclusively of basalt lava. Our lovely Hawaiian Islands are the classic example of this. If this superplume erupts under a huge pile of land crust like in Yellowstone National Park, you get a mix of felsic, intermediate, and mafic magmas and lavas. It's kind of like a battle between the ultramafic and mafic magmas of the superplume and the huge pile of felsic, mostly felsic rocks of the crust. That's a technical explanation, of course. Here we have a picture of the beautiful yellow felsic tuff of the Yellowstone Canyon. And here is the famous obsidian cliff in Yellowstone that's made of intermediate and felsic lavas. And here is the sheep eater cliff of columnar basalt lava in Yellowstone. You don't want to let your sheep get too close to that. Hi guys, now let's look at continental crashing when two continents crash into each other and see what kind of rocks are produced. In this picture you can see that the continent on the right has crashed into the continent on the left, and the continent on the right is riding up on the left continent and pushing its land crust down toward the mantle. This causes a lot of melting of this land crust, which is very felsic. And what kind of magma do you think will be produced by this? You are quite right. Granitic magma will be produced. Granite and granite-gneiss bodies that get close to the mantle may remelt into new granite. Other granite bodies will be metamorphosed into granite gneiss by the tectonic pushing and shoving of continental crashing. And other hunks of granite will be metamorphosed in part so that you get part of the rock that's granite and part of it that's granite gneiss. This kind of half and half or mixture rock is called a migmatite. Let's take a look at these babies. Here's granite, igneous rock. Here's metamorphic granite, which is granite gneiss. See the metamorphic banding? That's how you can tell. And here's a migmatite. It's kind of a combination of granite and granite gneiss. Those squiggly lines are saying, ouch, I've been through some stuff. There are a bunch of granitic plutons that were in place during the Akkadian orogeny, which was during Devonian time between 400 and 350 million years ago. The reason is because the Akkadian microcontinent, after it crashed way up in the northeastern United States, it slid down southwest to Georgia, North Carolina, and South Carolina, maybe even into Alabama, and is now called the Carolina Supertrain. And all the way along its sliding path, it produced granitic plutons. Let's look at a couple. Here we are in Acadia National Park, way up in the state of Maine, and we're looking at Cadillac Mountain granite that was in place during the Akkadian orogeny. Why is it sticking up now? Because everything on top of it has been eroded away. This beautiful stuff is granite, not granite gneiss. The reason is that the Alleghanian orogeny, which came after the Akkadian orogeny, did not occur way up here in the northeast. It happened further to the southwest, and so its smashing and crashing did not metamorphose Cadillac into granite gneiss. This beauty is called Looking Glass Rock. It is in the Pisgah National Forest of North Carolina, not too far from Brevard. Grammy and I did this hike about a year ago, and it's beautiful from the top. This is a granite and granodiorite pluton in place during the Akkadian orogeny of Devonian time. And let's end with one more famous pluton. This is Stone Mountain in Georgia. It was emplaced when Africa crashed into North America back during the Alleghanian orogeny. It is granite, not granite gneiss, because there has been no continental crashing events since Alleghanian to deform it or metamorphose it into granite gneiss. Perhaps those southern generals are riding away from the next crash as fast as they can go, which ain't really very fast. Okay, guys, here's a kind of summary of what we've been talking about, the rocks produced by different plate tectonic activities. Be sure to remember that these are just generalized guidelines that represents the most likely rocks that will be produced in abundance by a particular plate tectonic activity. And as a quick review, here's a list of felsic, intermediate, mafic, and ultramafic rocks with examples of each. Okay, most excellent rock buds, that's it for the rocks of plate tectonics. Thank you so much for watching. And if this video was helpful to you, please subscribe. And this is your Rock Papa saying to all my most excellent rock buds, happy rock hunting. Papa out.